Hi everybody, and welcome to Physical Particle Trapping. Thank you all for being here. Decades in the making, and so many people, our incredible lab, crew, worked very hard to bring you the most immersive and authentic testing experience we could. These are real devices, real particles, real trapping, so we're so happy you're here in this lab and seeing this presentation on your screen. So please enjoy, as we all made it for you.
When you first receive this wafer, you'll see that the devices are organized by rows and columns. Each row is designated by a letter. There are 11 rows, and so the lettering goes from A at the top of the wafer all the way down to K at the bottom. In addition to that, the columns are numbered from 1 at the right all the way over to 6 on the left. Each column on this wafer, from 1 to 6, has a different design. Here you can see the different designs numbered by column. All the designs should have the same functionality, but you might notice some differences in flow speeds as you vary which design you use. It shouldn't matter which design you use for your trapping, but something that you will have to consider is where to place the nanopore for each of these designs. A suggestion for where to place the nanopore is given in each of the pictures here. Now that we have a good idea of how these devices are working, it's time to start setting up for testing. You can start testing with any of the devices on the wafer, but I'll send a map along with the wafer that will show which of the devices are intact. The testing setup only requires the following materials. First, any devices that you want to test. Second, copper bead reservoirs, 2 for each device, along with the crystal wax used to mount those reservoirs. Third, a vacuum pump. And fourth, a syringe or micropipetter that can be used to place deionized water and analyte beads on the devices. A microscope is also convenient for observing the test. A convenient feature of this design is that the testing setup requires no lasers. All the particle trapping in the devices happens through passive physical trapping. Here you'll see that I've cleaved a wafer to prepare a few devices for testing and mounted copper bead reservoirs on those devices that I want to test with crystal wax. Before the device is ready for testing with particle samples, the channels must first be filled and any bubbles removed. I'll show you how this can be done. First, note which side of the device is the inlet and which side is the outlet. You can see an arrow on each device that points from the inlet to the outlet. When you're looking at the wafer in this orientation, it's pointing from the right to the left, as you can see on this device here. The initial filling of these devices will start from the outlet. We first connect the tube from the vacuum pump to the inlet side of the device that we want to test, the inlet side being the side with the arrow. Next, we fill the outlet side of the device with deionized water. Here's an example of what the initial filling of a channel looks like. Once the outlet reservoir is filled with deionized water, turn on the vacuum pump. I recommend leaving the pump on for about 5 minutes. This helps to remove any bubbles in the channel. The pump should remove bubbles from the inlet side of the channel. Bubbles on the outlet side of the channel won't affect the functionality of the device. Once the bubbles have been removed from important areas of the channel using the vacuum pump, the device is ready to be tested with analyte particles. Note that there are two ways of priming the channel. The first that I've shown you here is by pumping from the inlet side with a vacuum, but the second way is by pressurizing the outlet side after it's been filled with compressed gas, for example, compressed nitrogen. I've actually had more success with the pressurizing the outlet method, but I'll leave it up to you to choose which way you want to do. Disconnect the vacuum pump tube from the inlet reservoir. Fill the inlet reservoir with your sample particle solution. An optional step here is to empty the outlet reservoir of fluid. This promotes flow in the device. You can do it either with a syringe to suck the fluid out, or I often just use a piece of paper towel to suck any water out of the outlet reservoir. Next, connect the vacuum pump tube to the outlet reservoir of your device and turn on the pump. This will begin the particle trapping in the device. The amount of time to leave the vacuum pump running, pumping fluid and particles through the channel, depends on how many particles you need trapped at the trapping region. Here's an example of trapping in one of these devices. You can see fluorescent particles being trapped along the edges of the collection region. This section of the device acts as a filter to strain out particles and collect them near a center point where the nanopore can be placed. I've superimposed a picture of the device being used over the video so that you can better see where fluid is flowing in the device. The particles that you see being trapped here are 800 nanometer diameter fluorescent particles. Any particle this size or larger should be trapped in these devices, and some smaller particles will be trapped as well, but I haven't yet measured the minimum particle size that can be trapped. Here I'd also like to note that, as with priming the channel, there are two different ways of pumping fluid through the channel to trap particles. One of them involves pumping with a vacuum, like I've shown you, and the other one involves pressurizing the inlet side with compressed gas. I've found that there's more flexibility with pressurizing with compressed gas because you can use a pressure regulator to be able to manipulate what pressure you're using to pump fluid through. But again, I'll leave it up to you to decide which method to use yourself. The pressure that's used for pumping matters very little, as long as the pressure is high enough to allow fluid to continue flowing through the channel, trapping particles, but low enough that the membrane on top of the channel doesn't rupture. I've measured flow rates for the different designs, and those flow rates are shown here for the 6 different designs. These flow rates assume that the channel is pressurized to 1 atmosphere at the inlet side. So flow rates will definitely be different if you're using the vacuum pump method or if you're using a different pressure on the inlet side. Flow rates will also change as particles accumulate in the trap. And that's all there is to it. You now have particles trapped within a few microns of the nanopore. This design is still in progress, and there are still a couple of problems that I've run into, like bubbles and low flow. So if you test a device and it doesn't work as you expect, then I would recommend just moving on to another one, because another device on the same wafer will probably work a lot better. If you've tried out a few devices and are still having issues with bubbles and low flow and haven't been able to solve them, I would recommend resetting the devices in Piranha.
And if at any point in this process you have questions or I didn't explain something well enough, feel free to contact me. I'm here and I'm willing to answer any questions you have. I look forward to hearing what your results are.